Hey everyone, in this video I will present you my paper called New Bounds for the Flock of Birds problem, which was accepted to CSR2022. And the problem is as follows. As the title suggests, it is called the Flock of Birds problem, and there are n birds, and we want to know whether there are at least t birds for some threshold t. And we are kind of naturalists, so each bird is equipped with a sensor, and the sensor has kind of a low memory capacity, so it can only be in one of the Q states, or in other words, it just has log Q bits of memory. And what happened next is that birds from the flock, sometimes a pair of birds, come sufficiently close to each other so that their sensors can interact. And if this happens, both sensors detect that there is also some other sensor nearby, and each of these sensors can see its own state and the state of the other sensor, and then they update their states according to some predetermined transition function delta. It just takes a pair of states of two sensors before the encounter and outputs a pair of their states after the encounter. And your task is to program delta, right? Delta determines the behavior of the sensors. And you should also define a partition of the states into two kinds called 0 states and 1 states. And these two things, delta and this partition, constitutes so-called population protocol. So population protocols are algorithms in some sense for our problem. Okay, so our problem is kind of determine whether there are at least t birds. So that's our goal. But what does it mean exactly in this model? So to realize this, we just have to note first that we assume that birds pair with each other forever on. So it gives us an infinite sequence of pairs of birds, or in other words, an infinite sequence of encounters. And we also have to have some assumptions on this sequence, because if assume that just the same two birds meet each other over and over again, then you cannot extract nothing useful for your problem. So we will assume that so the sequence of encounters is quote realistic. So I will define it in one slide, but if it's in the intuition is kind of that infinite sequence has to look as it was obtained just by random tosses of coins. And so what it means that the population protocol solves our problem is that if the size of the flock is less than the threshold, then after some finite number of encounters, there is a place in the infinite sequence of encounters starting from which all sensors are always in 0 states. So in the intuition here is that the, sensors should converge to a consensus that the size of a flock is less than threshold. And similarly, if n is at least t, then for any realistic infinite sequence of encounters, it should hold that there is some place starting from which all sensors are in 1 state. And it should work for any n, so the size of the flock can be arbitrarily large, while you have the same memory capacity q. And it should work for every n. And then the question is, what is the minimal q such that there is a protocol which solves our problem with threshold t? And just to finish the definition of the problem, I have to define realistic sequences. But before that, let me just give you an example of a population protocol, just to give you an idea what actually one can do here. And consider the following protocol where all sensors initially have virtually, of course, 1 coin. And then when two sensors meet, one of them gets all the coins of the other one. So one is left with 0 coins and the other one with the sum of their initial quantities of coins. And let's say when initially if two sensors with 1 and 1 coins meet, one of them gets 2 coins and the other 0. But this happens unless they already have at least t coins in total, right? So they directly observe at least t coins. But initially, of course, there are n coins, where n is the number of birds. So if two sensors directly observe t coins, then they conclude that there are actually at least t birds. So the problem is solved. In this case, they transit into a 1 state. Initially, all sensors are in 0 state. So initially, all sensors think that they think that the size of the flock is small, is less than threshold. But of course, in the situation that I just described, these two sensors transit into start thinking that the size of the flock is at least the threshold. And then if these two sensors meet other sensors, they also convert this into thinking that so there is a unique 1 state which is kind of absorbing. So in total there are t plus 1 states. There are t states, t0 states, which represent a sensor can virtually have 0 coins, 1 coin, 2 coins, and so on up to t minus 1. And there is also a unique 1 state. So in this solution, Q is linear in T, and if n is less than T, then let me just note that this case is easy. So you can ask why this population protocol solves our problem. Well, if n is less than T, then just never can any sensor come into a 1 state, right? They will be in 0 states forever on, right from the beginning, no matter what is the sequence. We don't have to understand realistic sequences here. But okay, so if n is at least T, we have to, so I will return to this argument later in this video. So it's a good point to just at least give a definition. What is a realistic sequence of encounters? So formally, it's just an infinite sequence over the alphabet of all possible pairs of birds, if there are n birds, right? And it's called realistic if for any finite word over this alphabet, if any finite word over this alphabet has infinitely many occurrences in our infinite sequence. So it's a very weak requirement. And so once again, let's repeat the definition. What does it mean that a population protocol solves the flock of birds problem with threshold T? So once again, for any n, if the size of the flock is n, then all realistic infinite sequences of this flock have a place starting from which all sensors are always in 1 state. And similarly, with 0 states, if the size of the flock is less than T. And I just wanted to point out that I will be interested in protocols that behave as a protocol from the previous slide. So the protocol from the previous slide is such that if n is less than T, then no sensor can ever come into a 1 state, right? And I will call such population protocols one-sided. So I will study the following two functions, well, mostly the right one. So Q of T is the minimal Q such that there exists a population protocol which has Q states and solves the flock of birds problem with threshold T. And on the right, we have the same definition, but where we only take one-sided population protocol into account. So in this paper, we are actually interested in one-sided population protocol for the flock of birds problem. But of course, I will mention some results on Q of T as well, just for context. Okay, let me now provide more context for this problem. So population protocols are in fact a very well-established model in distributed computing. was inspired by some considerations in networks of mobile sensors, as our previous examples show, and also some consideration of chemical reactions, but probably it's most well known for its quite unexpected connections to logic. Namely, population protocols can be defined for computing predicates over natural numbers. And just in our case, in the case of the flock of birds problem, we are actually computing the threshold predicates. These are predicates that for a given natural number n decide whether n is at least some threshold, fixed threshold t. You can also define this not only for unary predicates like in the flock of birds problem, but for binary, ternary, and so on. So, and there is a theorem of Angloin et al. Which characterizes the set of predicates that can be computed by population protocol. It turns out to be exactly the set of predicates which is definable in Pressburger arithmetic. And I have my own analogy which is meant for making this result believable. So the main thing in the Pressburger arithmetic is addition. And in the model of population protocols, where you represent natural numbers like just piles of items, like in our case, we just represent a natural number n as just a flock of n birds, then with this representation, it is really easy to add natural numbers. You just like take two flocks of birds and just smash them one to another, and then you obtain one flock, and its size is the sum of two natural numbers. Okay, and the last point here is that one-sided population protocols, it's really easy to show. It's much easier than this theorem of Angloin et al. That they exactly compute threshold predicates, and also additionally the all zero predicate, which is kind of a threshold predicate where t is infinity. So this last point just justifies why we should be interested in complexity of population protocols for threshold predicates, because this is like they exactly correspond to this kind of predicates. Now, since this result of Angloin et al., I think there has been the two main research directions in this area, both minimizing two parameters of population protocols. One is obvious, the number of states, as we are interested in this paper also, and the other one, which I won't really provide much references, but the other is the time of convergence. But it's also very reasonable. You just want to minimize the time until all your sensors reach the consensus. But if we return to the number of states, we can just ask, so we are given a Pressburger definable predicate, then you can ask, what is the minimal number of states in a population protocol computing? In fact, people studied these problems not only for predicates, but for other problems like leader elections. So there is an immense literature here. I would like to mention one general result due to Blondin et al. It states that it's kind of a quantified version of the Angloin et al. Characterization. It states that any predicate definable by so if you have a Pressburger formula, quantifier free, so there are no quantifiers, but can have logical connectives, and it can have addition, comparison, and even modular gates, in fact, and it also has arbitrary constants, and constants are written in binary. And if then the length of all of this is L, the bit length, then this formula defines some predicate, and it turns out that this predicate can be computed by a population protocol with poly of L states, with polynomially many states in L. Now, what it gives for our problem. So in our problem, we are interested in computing the predicate n is at least t. So it's like already written here, but we should also specify t. To specify t, we need log t bits. So this result automatically gives us an upper bound on q of t, which is, I just want to remind, is just the minimal number of states in a population protocol that solves the flock of birds problem with threshold t. So Q of t turns out to be at most polylogarithmic in t, and so this is much better than we had on one of the previous slides, where we had like Q, which was about linear in t. But of course, not of course, but for these specific problems, there are a lot of other results, which for example, there is a simple counting argument that shows that Q of t is polylogarithmic in t for infinitely many t. But more precisely, it is at least square root of log t up to some log factors for infinitely many t. And the way you can show it is very simple. You just let's say you take some Q and you consider all and then you just count how many different population protocols you have with at most Q states. And then, you know, each of these population protocols can solve the flock of birds problem only for at most one threshold, right? And there are many thresholds. So for some of them, you will require many states. So that's the idea of this argument. And there is a much more difficult result of Scherner and Esparza, which shows that Q of t is at least log t for all t. So the difference is that this lower bound is for all t. No, but unfortunately, there is a huge gap. Now, what's with upper bounds? So Blondin, Esparza, and Ajax have shown that Q1 of t, so it's Q, but where only one-sided population protocols are taken into account, is at most 4 of log t. So on the previous slide, we had a polylogarithmic upper bound, but it turns out it's just logarithmic without any, not log squared or something, just 4 log of t. And of course, since one-sided population protocols are also population protocols, the same upper bound holds for Q of t. And also in the same paper, Blondin, Esparza, and Ajax have shown that Q1 of t is at least a log of t base 3. So now but this is only for Q1 of t. So for Q1 of t, for one-sided population protocols, the gap between the upper bound and the lower bound is just some constant multiplicative gap. And in fact, the goal of our paper was to kind of try to narrow this down. And before stating our result, I just would like to mention that there is a recent result of Scherner who have shown that Q of t is at most log of t for infinitely many t. But obviously, his population protocols are not one-sided because otherwise they would contradict the previous lower bound. So our result is that we have shown that for all t we have that Q1 of t is at least a binary log of t, so it's better than just log t base 3. And at most binary log of t plus the minimum of 2 quantities. One quantity is E, and this is the number of ones in the binary representation of the threshold. And the other quantity is Z, and this is the number of zeros in the binary expansion of t minus 1. And the corollary of this is in fact that the minimum of these 2 quantities is always at most binary log of t over 2. Because E is at most the number of ones in the binary representation of t minus 1 plus 1. Because when you add 1, you can only at most add one in the binary expansion. So E plus Z is at most the length of the binary expansion of t minus 1. So one of them is at most half of the binary log of t. So the corollary of this is that Q1 of t is between the binary log of t and the binary log of t with the 3/2 of the binary log of t. And in the final section of this video, I would like to give you some overviews of the proofs of my results. But first I have to give a slightly more convenient definition for arguments than one that I gave earlier. One that I gave earlier is more natural and less technical, but it's hard to argue with it. So let's recall the old one. So we had a definition of realistic sequence of encounters. It just means that all possible finite words occur infinitely often there. And then we say that the population protocol solves our problem if for every n, if n is at least our threshold, then for any realistic infinite sequence of encounters of n birds, there is a moment starting from which all sensors are in one state. And similarly, for 0 states, if n is less than our threshold. I would like to give an alternative definition, which only requires to consider finite objects. In fact, namely configuration graphs. What is it? So if I have a population protocol, its configuration is a vector in n in natural numbers to the q. So q is the number of states of pi here. And so a configuration just specifies how many sensors are in each state. And then I draw an edge from one configuration C1 to some other configuration C2 if there is some encounter which brings C1 to C2. And then we obtain for every n, if we just restrict ourselves to configurations with n birds, we obtain a configuration graph of our protocol of order n, which I denote by gn of pi. And then there is the following result that shows that we could alternatively define what does it mean that pi solves our problem with threshold t. So it's the same as the following requirement. For every n and for every trap in the configuration graph of pi of order n, there should be something to hold. But what is a trap? A trap in our graph is a reachable from the initial configuration, strongly connected component, which is impossible to leave. Basically, it means that this is some set of configurations such that it is pairwise connected. So from each configuration of this set, you can reach any other configuration of this set, and it is impossible to reach any other configuration. So for every n and for every trap in Gn of pi, you should have the following. So it depends on whether n is at least t or is smaller than t. So if n is at least t, then all configurations in all the traps must have only one state. There cannot be any sensors in 0 states. Similarly, if n is less than t, then all configurations in all of the traps must have only 0 states. So let's try to understand why these two definitions are equivalent. And this relies on the following lemma. It states that if I consider any infinite realistic sequence of encounters, then I can run my population protocol over it, and then I obtain an infinite sequence of configurations of my protocols. And then I consider all configurations that occur infinitely often in this sequence. And I claim that this is a trap in the corresponding configuration graph. Okay, let's try to understand at least why this lemma implies the theorem, the equivalence result. The more easier is to show it from right to the left. So assume that for every trap in Gn of pi, we have that there are only one states, right? And let's consider the case that n is at least t. In the other case is similar. So then we have to show that if we run our protocol over any realistic sequence of encounters, then from some moment, there will be only one state. So why is that? This is a really simple consequence of the lemma, right? Because if I run my protocol over a realistic sequence of encounters, then all the configurations that occur infinitely often are in some trap. But we know that in the trap, there are only configurations that have only one state. So this means that after some finite prefix, all configurations that I have obtained by running my protocol over this sequence of encounters have only one state. Yeah, and for the other direction, if I have a population protocol, it solves our problem. I have to show that then every trap in its configuration graph satisfies these properties. So if, let's say, again, n is at least t, then all configurations in all of the traps have only one state. So I have to consider an arbitrary trap, and then I have to show that it has only one state. So first, I know that there exists some sequence of encounters that brings me to this trap. So I go through this sequence. So now I'm in this trap and I cannot leave it. And then I just consider any realistic sequence of encounters after this finite sequence. It's even if I append this finite sequence, this will be realistic because realistic sequences are closed under adding or removing any finite prefixes. So I know that since my pi solves my problem, then starting from some moment, I will have only configurations that have only one state. So in particular, all configurations that occur infinitely often in this computation have only one state. But by the lemma, the set of all these configurations should be a trap. On the other hand, it should be a subset of our trap that we came in first, right? But it is impossible that one trap is a proper subset of the other trap, right? Because otherwise we could leave a smaller trap. So this means that all nodes, all configuration in my trap that I'm interested in occur infinitely often. It means that they should only have one state by the definition of what it means that pi solves our problem. And finally, how to prove the lemma. So we have to prove that if I have a realistic sequence of encounters and I consider the set of all configurations that occur infinitely often, and first I have to show that, well, they are pairwise connected, because if they occur infinitely often, then for any configuration that there is a moment in future that any other, so that all other configurations occur. It means that the corresponding, it means that they are pairwise reachable. And the only thing I have to show is that no other configuration is reachable from them. And this holds from the following fact. So if I have some pairwise connected set of configurations, and I call it S, and I can leave it, I assume this for contradiction, then there exists a single finite sequence of encounters that leaves S from if I start applying it after any configuration of S. So the point is that the same finite sequence works for any configuration of S. So why is that? Okay, so you know, if you can leave S, then there is some finite case such that you can leave S in k steps for any configuration of S. So there is if you just start, you know, picking your configurations at random, so there is a positive probability that you will leave S in k steps. Okay, but it may be small. But then repeat it again. So I mean, in 2k steps, this probability will be slightly bigger. And when you just repeat and repeat over and over again, this probability becomes closer and closer to 1. So we can just repeat it sufficiently many times so that this probability is such close to 1 that, you know, by the probabilistic argument, you can fix some choice of random coins so that, you know, the resulting finite sequence works for any starting configuration from S. having this alternative definition, we can now finish the argument that the protocol that has been considered in the previous slides works correctly. So just a quick reminder, what was this protocol? So this was a protocol where sensors pass each other coins. So when two sensors meet, one of them gets all the coins of the other one, unless they have at least T coins in total. In this case, they are converted into the one state, and they also convert all the other sensors they meet into the one state. So when the number of birds is smaller than T, then this case was easy. And now we can finish the case when n is at least T. So according to our definition, we have to show that any trap in the transition graph has only one state. Okay, so just consider any configuration in this trap. So it's not hard to see that we can actually bring one of the sensors into the accepting state, into the one state. So just take any non-empty sensors and let it meet all the other sensors one by one. Eventually, this sensor will collect all the coins until you already will observe at least T coins. And then you can just let this sensor, which is in the one state, meet all the other sensors. And so while you are in the trap, you can reach a configuration in which all states are, in which all sensors are in one state. But since you're in the trap, then it means that you can reach all configuration of this trap again. And this means that, and you can now just observe that once all sensors are in the one state, then they will always be in this one state. So this basically means that in the whole trap, there are only one states. And this is exactly is required by our alternative definition. And so let's now talk about our upper bound. So it states again that Q1 of T is at most binary logarithm of T plus the minimum of two quantities. E is the number of ones in the binary expansion of T, and Z is the number of zeros in the binary expansion of T minus 1. And to prove this, we actually develop two different protocols, one with log T plus E states, and the other one with log T plus Z states. And we just, for any case, we take the best one. So I will consider two extreme cases in this overview. One extreme case is when T is power of 2, so it's some 2 to the D. In this case, both E and Z are actually small, because in 2 to the D, there is only one in the binary expansion. And in T minus 0, which is 2 to the D minus 0, there are no zeros in the binary expansion. But okay, so in fact, this case was, and the claim is that we can solve this case with just D plus maybe some constant number of states. And in fact, it was known well before our paper, but the point is that the main technical contribution of our paper can be shown in the case when T is 2 to the D minus 1, so its binary expansion consists only of ones. So E is large, but Z is small, because Z is the number of zeros in the binary expansion of 2 to the D minus 2. And there is only 1 0. So there is, I think there is a nice technical trick which allows us also to solve this using only D states, not 2D or something like this. So, but I will start with the case 2 to the D. This is a classical protocol, but still the protocol is as before, where sensors passed each other coins, but now sensors can only hold powers of 2 coins. So one sensor only gets all the coins of the other one only in the case when they have the same number of coins. So if they have 1 and 1, one of them gets 2 and the other one gets 0. When we have 2 and 2, this gives us 4 and 0, and so on. So we can only, in this way, we can only have powers of 2 or 0. So a sensor just has to basically remember which power of 2 it holds up to 2 to the d, or if he holds 0 coins. So it's around d states of memory. Now, and the condition, well, how the sensors behave. So when two small powers of 2 meet, one sensor gets 2 times the sum of these 2 powers of 2, and the other one gets 0. And if two sensors with 2 to the d minus 1 and 2 to the d minus 1 coins meet, they are converted into the one state, and then they convert all the other ones. Okay, now if so the argument is twofold again. So if n in the number of birds is smaller than the threshold, which is 2 to the d, then the argument is the same as before, just nobody can ever come into the one state, because the total number of coins is preserved throughout the protocol. And to come into the one state, you need to see at least 2 to the d coins, and you have less than this. So this is easy. And okay, let's now show what happens if n is at least 2 to the d. So we, according to our new definition, we have to show that any trap has only one state. So we consider any trap, and as before, it is sufficient to bring some sensor from some point of this trap into the one state. So how can we do this? So we consider some configuration of our trap, and then we consider a configuration which is reachable from it, and minimizes the number of non-bankrupt sensors. So a sensor is bankrupt if it has just 0 coins, and others are non-bankrupt. Okay, so we consider this minimal configuration reachable, and the claim is that there has to be 2 equal powers of 2 in this configuration, because otherwise we can have at most 1 plus 2 plus 4 and up to 2 to the d minus 1 coins, which is less than 2 to the d, and initially we have at least 2 to the d coins. Okay, so we have 2 equal powers of 2. Then if it is 2 to the d minus 1 and 2 to the d minus 1, then we can pair them, and we can bring these 2 sensors into the one state, and we are done. Otherwise, if these are smaller, if we have 2 smaller equal powers of 2, then we can actually, by pairing them, we can decrease the number of non-bankrupt sensors, because one of these 2 will become bankrupt. So it's impossible, and we have shown that we can bring one of the sensors into the one state. Okay. So this was case when t is 2 to the d. But what to do when t is 2 to the d minus 1? We employ the same protocol where we have powers of 2, but there is a slight modification. So when we have small powers of 2 and they meet and they are equal, then the protocol behaves exactly as before. But there is only one exception, is that when 2 sensors with 2 to the d minus 2 coins meet, one of them as before gets 2 to the d minus 1, so all the coins, and the other one gets not 0, but just 1 coin out of nowhere. So it's a main technical trick here. And okay, and for completeness, when 2 sensors with 2 to the d minus 1 coins meet, they both come into the one state, and then they convert everybody as before. So again, we have to show 2 things. That first, in the case when n is smaller than our threshold, it is impossible to come into the one state. So why is that? Okay, well, initially we have, so to come into the one state, we should have at least 2 to the d coins, right? Because the only way we can come into the one state is when we have 2 sensors both with 2 to the d minus 1 coins. But initially we have less than that. In fact, we have less than z minus 2. So we have less than even 2 to the d minus 1. So if in order to come to the one state, there has to be a coin out of nowhere at least once. So let's consider a moment when it appears for the first time. Then we get one sensor which has 2 to the d minus 1 coins. Let's consider the rest of the coins. There is one extra coin out of nowhere, and then before that we also had n minus 2 to the d minus 1. Besides this besides this sensor with the largest number of coins. So let's consider this number, n minus 2 to the d minus 1 plus 1. So it is smaller than, well, n is smaller than 2 to the d minus 1. So you also take minus 2 to the d minus 1 and plus 1. So the point is that besides these 2 to the d minus 1 coins, there are less than 2 to the d minus 1 coins. It means that you can never have two sensors with 2 to the d minus 2 coins again, so you can never produce one more sensor with 2 to the d minus 1 coins. And to come into the one state, you need at least two such sensors. And finally, we have to consider the case when the number of birds is at least t. Then again, the argument reduces to showing that for any trap and for any configuration from this trap, we can bring somebody into the one state. So we do this as follows. So we take any configuration from a trap, then we consider all configuration reachable from it. We first consider one which maximizes the total number of coins. You know, throughout the execution of the protocol, the number of coins can increase, right? But it's always bounded, right? Because any sensor can hold just at most 2 to the d minus 1 coins. So the total number of coins is bounded. So we just consider the maximal possible value of coins. And after we did this, then we also minimize the total number of non-bankrupt sensors as before. Now, so we take this maximal minimal configuration. And we can assume without loss of generality that there are no two sensors which have the same powers of 2, non-zero sensors. Why is that? If they have two equal small powers of 2, then we can decrease the number of non-bankrupt sensors as before by pairing them. Okay, if they have 2 to the d minus 2 coins both, if they both have this number of coins, then we can increase the total number of coins by pairing them and by getting a coin out of nowhere. So it's also impossible. And the only possibility is that we have two sensors both with 2 to the d minus 1 coins, but then we are done. This is all we want. Then we can bring them into the one state. So maximally we have in this configuration 1 plus 2 plus and so on 2 to the d minus 1 coins. And this is exactly t, right? Well, now, but initially you had also at least t coins, right? So in particular, this already shows that, you know, you only have to consider the case when n is equal to t, but that's not really helping. Let's finish the argument somehow. Okay, so we have maximally we have 1 plus 2 plus 2 to the d minus 1 coins. Okay, but maybe we don't have this last 2 to the d minus 1 coins, but then we have less than t, strictly less than t coins. And in the beginning, we have at least t, so that's impossible because we can only increase the number of coins throughout the protocol. So we should have exactly 1 plus 2 plus up to 2 to the d minus 1 coins. But then the point is that when, so it means that when you recall that when 2 to the d minus 1 is created, we also create a coin out of nowhere. So it means that the current number of coins is bigger than it was in the beginning, but now it is exactly t. So in the beginning it was less than t, and it's a contradiction because we must have had at least t coins in the beginning. So then this case is also finished. Finally, I will present the lower bound, and I think I just can give the full proof of it. So it states that Q1 of t is at least the binary log of t. And to show this, okay, we consider an arbitrary one-sided population protocol pi, which solves our problem with threshold t. And then, and assume that its set of states is S. And we have to show that the size of S is at least a binary log of t. To show this, we define some function f whose domain is S, and then we will use the fact that the size of S is at least the size of the image of S under F. Then we will lower bound f of S. So what is the f? If S is some state, then I define f of S to be the minimal n, such that if we start from the initial configuration of n birds, there exists some sequence of encounters which brings one of the sensors into the state S. So I will just briefly say the same by saying that S can occur from n birds. Okay, once again, the size of S is at least the size of f of S, and f of S is just some set of natural numbers. We have to show that there are at least binary log of t elements. So what we know about this set? First, we know that 1 belongs to this set because of the initial state, right? Because initial state is there initially, right? So even if you start with from the configuration of just one bird, then you already have the initial state. So 1 is equal f of the initial state. Now, I'm also claiming that t belongs to f of s. So why is that? Okay, t is my threshold, so I consider a configuration of t birds. Then I just can consider an arbitrary realistic infinite sequence of encounters from this configuration. Okay, and all I need is that it is possible to bring one of the sensors into the one state from a configuration of t birds, right? And then I just consider this one state, so it can occur from t birds, but it cannot occur from less than t birds because our protocol is one-sided. So if the number of birds is smaller than the threshold, then it is impossible to get a one state. So because of this one state, we have that f of this one state equals t. So t belongs to f of s. And finally, to show that f of s is large, we show that f of s cannot have large gaps. So any two consecutive elements of f of s are sufficiently close to each other. More precisely, if I have two consecutive elements of f of s, a and b, and a is a smaller element, then b is at most 2 times larger than a. And this clearly implies, so since you have in your set f of s, you have 1 and you have t, and each next element is at most twice as large as the previous element of this set. So between 1 and t, you need about binary log of, you must have at least the binary log of t elements. So it remains to show the lemma. So here it is. We have to consider two consecutive elements of f of s, and we have to show that the bigger one is at most twice as large as the smaller one. So we consider b, the larger one. We know that it's in the image of f of s under f. Yeah. So then we consider the minimum number of steps such that the minimal number of encounters such that these encounters can produce some state S such that f of s is b, and I mean produce from the configuration of b birds, right? So since there exists some s with f of s equal b, so there exists some finite sequence of encounters that does that. Then we just consider the shortest such sequence and let the corresponding state be S. So we know that S cannot be here just in the beginning, because S is not the initial state. Because otherwise we would have that f of S is 1, but it is B. So S was produced via an encounter of two sensors. Let's say one of which was in the state S1 and the other in the state S2. Now, what we know about S1 and S2? We know that they are produced from B birds in less number of steps than S because of the minimality of S. And this implies that f of S1 and f of S2 are not equal to B. But still they can be produced from B birds. This means that f of them is at most B, but it's not B, so it must be smaller than B. Okay, but the predecessor of B in the set f of S is A. So we conclude that f of S1 and f of S2 is at most A. All right, and what remains to show to finish the proof is that f of S is at most f of S1 plus f of S2. That's written on the bottom at the right. So then we are done, because f of S1 is B by definition, and we already have seen that f of S1 and f of S2 are at most A. So why do we have this inequality? So S1 can occur from f of S1 birds, and S2 can occur from f of S2 birds by definition of f. So if we consider f of S1 plus f of S2 birds, and we split these birds into two parts, one with f of S1 birds and the other with f of S2 birds. So the first part can give us S1, and the other part can give us S2. And then these two sensors in these two states can, as we already know, they are producing S. We conclude that S can occur from f of S1 plus f of S2 birds. And this by definition means that f of S is at most f of S1 plus f of S2. Yeah, so this is the end of the proof, and that's also it for this video. So I hope you like it. Thank you very much.